Good morning, afternoon, good morning. I'm Dean Tribble. As you can tell, I'm not Mark Miller, as said here. He sends his regrets. His biological substrate was insufficiently encapsulated, and so he has a fever. He was going to talk about some of the lower level details to be able to do migration of computational units from one chain to another and one shard to another and so forth. I instead am going to talk about going on vacation. This is a problem that Andrew Miller raised to articulate an issue with sharding, originally in Ethereum, but it's the kind of problem that's been around for a long time. People have been doing, atomic transactions for a long time in order to do commerce. And the simple articulation of the problem is, I'm going on vacation. I need a hotel and a train ticket. If I can't get a train ticket to the place where my hotel is happening, then I don't want the hotel reservation, and vice versa. Ironically, I found out about this thing when I had bought a plane ticket and failed to get a hotel and had an exciting result. So this is a very memorable problem to me personally. Now, the simple implementation of this that we're all familiar with is I just start a transaction. I go make a call to get a hotel reservation. I go make a call, it finishes and succeeds. I go make a call to get the train ticket. It finishes and succeeds. And then I commit the transaction. Very straightforward, very easy to understand. People would love it if the world works that way. And indeed, when you're on a single machine in your local environment, it can work that way. And of course, if there's other transactions happening at the same time and they conflict, you end up aborting, but because it's a transaction, you will end up purchasing neither the train ticket or the hotel reservation. But as soon as you start having to do this in a distributed context, then it gets a lot harder, especially when you add in the Byzantine environment of blockchain. And so, distributed atomicity, fundamentally, in the early 90s, the internet was coming out, people were starting to build large-scale e-commerce systems, and they really, really tried hard to be able to use distributed atomic transactions for a lot of commerce. And there's a bunch of problems with them. And we looked at that, we built a lot of systems, and then you step back and go, how does the real world work when they run into this problem? How does a bank take $1 from one bank account that has $1 million and transfer it to another bank account? And they don't do it with an atomic transaction. If they did so, what would happen is they would grab a lock on the $1 million account, debit it by $1, but it's still locked in the transaction. Go over here, grab a lock on this account, update that balance, have a bunch of messages go back and forth, and finally agree that they can proceed, and now you can do other transactions on your $1 million account. Of course, that last message, as several presentations in the last day have pointed out, that last message to say, yes, I'm really done, go ahead and release it all, we finished the transaction, that last guy has an uncompensated option and could simply sit on that. So now, you can't use your $1 million account because in your banking system, it's locked up in this distributed transaction, and until that time's out, you're stuck. So what they do instead is they do a local transaction. On this $1 million account, I do a local, very fast transaction, completely under control of the first bank, pull out $1, and I'm done with that transaction. Then there is this payment that can take time to transit over the network, can take a lot of messages to agree that, yeah, I really meant $1, it's signed, we're good. And on the other end, it's received, and there is another local transaction to update the balance so that the $1 goes in. But there's a real latency there that really surfaces and is visible to us, the customer, and is something that we can reason about and talk about. And so that's the environment in which commerce happens across large-scale human industry now, and indeed that's reflected in how commerce happens between existing online businesses doing transactions. So we have myself, Agoric, my company, are building technology that addresses that. Where do we come from? We did some of the original Agoric Open Systems papers. We're software agents building and participating in markets. Those papers were out in 1988. Since then, several of us have built, have driven key security elements or invented key security elements that have gone into JavaScript and other programming languages, built brokerage information systems, payment systems, VoIP systems, all sorts of different kinds of large-scale, real production distributed systems. And almost all of them, we ended up heading towards an asynchronous world because the world is fundamentally asynchronous with little islands where you can get sequential programming and synchronous activity. And so we had to figure out how to solve a lot of these problems in an asynchronous world. So that's what I'm going to talk about going on vacation in an asynchronous environment. So the system that we're working on, and I'll provide a little bit of context and then we'll dive back into smart contracts. We see the world where, you've got individual machines we call solos, solo machines, where it's on my cell phone or a laptop or a server. You've got permissioned clusters, quorum machines, whether that's Hyperledger or any of those others, local cluster machines and so forth, and finally public chains. But in some sense, the quorum machines and public chains, they're making new execution environments, new machines out of agreement rather than silicon. There's a lot of technology to make them fast and secure and exciting, and they have vastly higher integrity, but fundamentally things you could do between individual machines you can do between these machines that are built out of agreement. Above that, we then have a computational perspective with these individual, what we call VATs, which are units of sequential execution with atomicity that can be relocated on different compute environments, on different of these underlying machines, and they have asynchronous communication between them. And that's the area that Mark was going to talk lots about from here on up. And then above that, we build the ability to talk about those easily in a programming language. Our focus is, of course, enabling the vast world of millions of programmers out there that are not yet able to do smart contracts. Our goal is to enable them to do that. So we reflect a security model up into a programming language that they all know, JavaScript. And we can talk lots more about that. But we have a security model that we can enable them to build smart contracts in JavaScript and do secure distributed messaging between these islands of sequential programming across the network. And so messages can flow between them, writes can transfer between them, and so forth. So we can build on top of that then, finally, a framework of objects of reusable components for building smart contracts. And so I'm going to talk about the component approach to how you would solve the asynchronous, asynchronous train and hotel problem. So I mentioned the security model. There's the identity-based model, which I'm not going to talk about. There is another security model called the object capability model. It comes from a tradition of secure operating systems, SEL4, Midori from Microsoft, Kikos, Eros, Kyotos, and so forth. And it's got a bunch of very detailed technical requirements in order to implement it, in order to implement a transferable, unforgeable authorization to use the object that it designates. But at a programming language level, where most people will be building smart contracts, it just surfaces as simple encapsulated objects. And then out of those objects, we have patterns that we've designed and built over the course of many years to recover the ability to do security behaviors like, role-based access, authorization, authentication, all the kinds of things you expect, but we can do so with extremely strong security. And then on the smart contract side, or in the economic side, similarly, you have patterns of objects, just the straight kinds of things that millions of programmers build in JavaScript and Java and C# and everything else, to accomplish economic goals, and train hotel being one of those. But it looks just like programming. So a simple example, this is JavaScript, would be, I've got a concert, I've got guards at the entry and exit gates, they've got a clicker to make it to maintain a count of people inside the venue. Very simple toy example, but there's a count entry that increments the count, a count exit that decrements the count. And now I'm going to make that available to my guards. So of course I create one of these counters, and then here I'm using a JavaScript shortcut where I can just pull off the count entry as a separate object, but that's just JavaScript. It's fundamentally, here's a separate object which is the ability to increment the count, and I send that to the guard. I didn't do permissions, I didn't add identity entries, I didn't do it. I already have a reference to the guard, I send him the thing, and now he's able to click the counter. And when he goes off duty, he can take the counter and hand it to his replacement, and now his replacement can click the counter as people come in or go out. And so that's a simple how the object model surfaces engaging in authorizing people simply by going through the process of doing the interaction you expected to do with them. And you'll see a little bit more of that later. So now I'll lay some of the groundwork for the smart contract framework. that out of which the other elements here for doing, train, hotel, and reservation is based. So we have the objects that the ledger surfaces in, if you will. We have purses, we have mints where you can mint new currencies, and have purses that are individual accounts within that currency. So on the right, I'm making a concert. I have a digital good, which is the right to get into the concert. So I make a mint for my concert tickets. I'll talk about issuers on the next slide in a moment, but it's a lot like a brand for this. But then I mint a new ticket. Now I've got one concert ticket, and I return it to whoever it was that called my smart contract. Or in the last line there, the last section, I send it to Carol, and Carol does whatever she does now that she's received a ticket. But these are just objects. So now I'm going to introduce that first pattern that I mentioned. If I just send Carol the ticket, now she's got the ticket reference, and I've got the ticket reference. In our distributed environment, I might have sent Carol the ticket running on another machine across the network, but she's got a remote proxy reference to wherever that ticket was, as do I. What does she do in order to make sure she really has the ticket? This is where issuers come in, and this first thing. So what is an issuer? It's like a brand for one of these currencies or for any of these digital assets. It lets me figure out, this thing you gave me, is it really one of the types of things I was looking for, right? So it's got, the most important operation on it is get exclusive. So I hand the issuer a purse that contains, putatively, it's a purse containing a concert ticket, and I call get exclusive on the issuer for the concert ticket to that venue. So Shoreline has a web page. I got the issuer there. If your tickets don't pass this issuer saying yes, I can really get exclusive on it, then it's not actually a ticket to that venue, and it was a fraudulent ticket. So I take the issuer, I say get exclusive, and that does two things. It gives me a brand new purse, a brand new container with that concert ticket where I know that I am the only holder of that ticket. So whoever sent it to me couldn't care less. Their access is essentially revoked. I'm the only holder in the world of that ticket, so I know I have exclusive access. And I have exclusive access if and only if it was actually a ticket that was created by that issuer. So it was actually a concert ticket at the venue that I was interested in going to. And so that's that important step that now I can do transfer rather than just sharing of a pointer. Okay. So Carol's received ticket operation, she gets this thing that is putatively a ticket, but might be rights to a bucket of apples, who knows? She does get exclusive, and now indeed it succeeded and gave her a ticket, so she returns a payment to me, right? And so down at the bottom is where I would have minted a ticket, sent it to Carol, and I get her answer, and I get a payment, and I deposit it into my account. And that would work, as long as Carol actually returned me a payment. In this case, I was a little naive. I sent it to her, and she, in some sense, has the uncompensated option to go to the concert without ever paying me, right? So what do I do? So that's an example where commerce can succeed, but it's not safe, right? It's not, I wasn't able to arrange to protect myself in that arrangement. Okay, so now enters the first or another reusable component, which is in itself a smart contract, but here I'm using it just to engage in transaction, which is an escrow agent, an escrow exchange agent. Okay, so now instead of just sending Carol the ticket, I create this escrow exchange agent where it's only going to, where it has two sides to it, and they're essentially symmetrical, but I will create it saying the two things participating in this exchange are things which are tickets and things which are money, right? So concert tickets and money, I'm going to make a transaction about that. That's those first two arguments, and I've got these two sides. I send one to Carol saying, here's the place where you put in money and you'll get out tickets, and I keep the side which says, here's the place I can put in a ticket and get out money. And then I say, I mint a new ticket, here's an I do concert ticket, I stick it in there and saying, you can give it to the other side as long as I get my ticket price and dumped into my bank account. And so that's what that last line does. And Carol does approximately the same thing on her received ticket side. Instead of getting just a ticket, she gets the ability to participate in an exchange. Or does she? She wants to check. She does exactly the same kind of get exclusive, so she knows she's the only one participating in this exchange, and it is indeed the escrow agent contract that she believes in and trusts to actually engage in escrow. And then she says, great, here's my payment. You can only give it to the other side if they give me an actual concert ticket, right? Or an actual, stock or option or whatever it is that I'm buying in this exchange. And now, once both of us provided the right good, we'll be satisfied. I'll get my money, she'll get her concert ticket, right? And so we're both protected in that exchange much better than if we weren't otherwise. Now, just to be clear, most of this would be absorbed into the infrastructure. Most of this would be in components people are using. I'm showing you the low levels of how this is all built up. Okay. So now you're all ready for the implementation of, no, sorry, I'm not going to go into the implementation. But I will talk about how the escrow exchange agent works. Because it's simple, and what's cool is how it is simple. So fundamentally, there's multiple parties participating in escrow, but we'll just talk about two. And I'm sending my good to Carol, she's sending her good to me. So we create, internally there is what we call a transfer object, where when I put my good in, it does an internal get exclusive, and inside the escrow agent holds on to exclusive access to the concert ticket that I provided. So now I don't have it anymore, it got transferred into the escrow agent, which is what you expect an escrow agent to do. Similarly, and that's the first stage. Similarly, there's another transfer that'll be going the other way for Carol to put in the money. Right? Once both of those have succeeded, then the escrow agent that contains those two transfers will say, okay, we go on to stage two. But the escrow agent gets to do that where all that moving the money in is asynchronous. But once it happens, now the escrow agent can locally and atomically make a decision that says, yep, I've got everything I need. Let me asynchronously deliver the goods to the counterparties. And so at that point, the escrow agent invokes stage two, which takes the money from the internal escrow purse and hands it off to the destination. If there was a failure, either side gave stuff that did not match the goods. I said I wanted to be paid in dollars, and she paid me in a bucket of apples. Then the escrow would fail, and so what will happen is the abort runs, which simply turns around and all of the escrowed goods are returned to the sender. And escrow finishes with no one losing anything. So that's how it works. As I showed you before, it's 20 lines of JavaScript code. It's very straightforward. I'll add one more, and then we'll get back to going on vacation. And everyone has to do that last bit of work before going on vacation. So a covered call. What's a covered call, right? A call is an option, and we can use it generally across any digital good, but it is a bounded time right to purchase the good. In our system, that's represented as an object, so there will be a covered call object. And more importantly, in order to be able to build a world of growing contracts built on other contracts for nice decentralized open finance or applications that span different verticals, you want the contracts that you make to be themselves other goods that participate in the market. So indeed, the covered call wants to be itself be a digital asset that can participate in all these other smart contracts. So how does it work? Well, it makes a new escrow for the desired contract, because at the end of the day, if the covered call gets exercised, I'm going to want to go through the same escrow that Carol and I went to for the concert ticket. And then inside the covered call, we take the good. Let's say I've got a concert ticket and I'm going to make a covered call for many thousands of dollars. If I can sell my, Barbra Streisand or Adele ticket for $10,000, then great, I'll take the money. Otherwise, I want my ticket back and I'm going to the concert. Right? And so I need to take my ticket, put it in that side of the escrow agent on the ticket selling side. And remember, this is symmetrical, but one side is specific to each of the resources. So I put it on the ticket selling side, and I wrap the ticket buying side with an object that participates in this same get exclusive, and it just turns exercise the option into take the money, stick it in the escrow agent, and the transaction completes. So all the covered call is essentially a prearranged escrow that has a timeout and has and it is a covered call because the good is already escrowed. And so that means the promise that you can buy a particular good for a particular price is covered by the fact that the good is already there and ready to go. And when the time runs out, it would cancel the escrow and the goods would be returned to me, so I can take the concert ticket and go myself. And because this object also, this covered call also has the get exclusive, it participates in the whole contract ecosystem. Okay, so back to the train hotel problem, because you're all ready to go on vacation or at least go to lunch. The simple async solution for that, now it looks a lot like the escrow agent did, which is that the exchange manager that wants to get both of these things, it requests asynchronously the ability to get a option, a covered call on the room reservation, and a covered call for the train ticket. So that means is the service at the other end for doing room reservations, that's got to take the actual right to be in the room, escrow it inside of that covered call, and hand me back the sell side so that so I can see that I have the actual option and could claim the room for the price demanded by that transaction. So once I've asynchronously gotten those or any other options that I need, now that process can decide locally and atomically, oh, I've got the room, I've got the train ticket, go for it, right? So now it is decided that it's going to go for it. It can now asynchronously exercise those options to go and collect the room and actually get back the room reservation object that will give you the ability to unlock the room or whatever, and the train ticket. Right? And so we've got this asynchronous setting up, local atomic decision, asynchronous consequences going out. Now, it's a little different than the atomic transaction solution. One of the things that the atomic transaction was doing is it was hiding from the program all of the communication details, all the latency details, and so forth. That looks like a good thing. It looks like that's simplifying. The problem is those details are actually important, right? When the bank is transferring a dollar, they want to know where it is. They want to know how long on average it takes. They want to be able to decide to use a different courier because the transaction clears faster. And the same thing here. By actually exposing this in a way that I can hide from normal developers, and we'll come back to that, but by exposing it, we now have many more opportunities for commerce. For example, I'm going on vacation. I don't really care whether it's city X or city Y. So I'm going to make these asynchronous requests for both, get a bucket of options back, and then figure out what my favorite pair is, right? So, I could go tonight or go tomorrow. I could end up in Carmel or end up in San Francisco. I like this combination. Let's exercise those options and throw away the others. Now, the more options I get, the larger a fraction of my eventual purchase price I might have to spend on those options. But that's a choice I get to make dynamically because of it. I have exposed this behavior. Similarly, I can look at, okay, every time I go to that hotel provider, it takes, a minute to get a transaction. When I go to that one, it takes 10 seconds. I like the 10 seconds. It makes my web page faster. I'm going to start using those. And I can see that because the details of that interaction are exposed. Okay, so that works. We know this solves the problem. We've built plenty of systems that have this kind of asynchronous collaboration, and it is certainly the case that when you go into any of the websites that you can buy travel, you're not getting an atomic transaction on all these things. You're grabbing different things and getting a short-term reservation and then being able to close it at the end and finally confirm it, right? And so we can do this. But we sure don't want, but it does look more complicated than that simple thing we did at the front. And we sure don't want most programmers to have to do this. This is what's important about having a framework, right? There's a range of different skills and a range of different expertise across the millions of programmers that we want to appeal to. And there are the people that can do an incredible job of these composable covered call options and leverage positions on them and all the kinds of things that might grow into large scale financial and travel and purchase and all those kinds of things. And then there's the people who are domain experts that know what business they're trying to do. And what we want to make sure is someone doesn't have to be expert at all of these things in order to be able to roll out a DApp that does real business. The nice thing about this is that algorithm that does that fancy get some options, make sure they're all there, and then execute them, that too, just like the covered call, was a full market participant that I could pass around, sell through Extra Exchange, or put up on an auction. That ability to do a multi-goods purchase is something that an expert can wrap into a component, and then someone who just wants to have a site that's doing decentralized planning for parties can use that, find the right issuers of rooms, music, food, and valet service, and say and get all of those. Tell me what date you got. We're throwing a party, and they don't have to be an expert, an economist. They've got to know what's good music and how to get a good DJ. So that separation of concerns is hugely important for growing the world of smart contracts and enabling smart contracts to really break into mainstream usage, whether it's large, small, or highly decentralized business. You want people to not have to be able to use the smart contract products of third parties in their applications. And Fundamentally, from our perspective, the solution to that is an async infrastructure. The world is async. The world of commerce is async. We can build local islands of execution, but what we want is an architecture that lets us, that naturally matches the nature of the world. That's what will help a lot more people succeed at building large-scale smart contract systems. Thank you very much. And I realize I can't send you all on vacation, but we'll have questions here, and then we all get to go to lunch. So that's as good as I can do here.
Any questions?
Hi, Dean.
Hello, Nathan.
So one of the slides showed solo computers and quorums and blockchains. How does that connect to the layer you were showing us? For example, I'm thinking of public blockchains because I love them. Let's say Ethereum.
Yes.
If it's plugging into one of those components, how does it account? How does the smart contract layer you're describing account for things like rollbacks or other complexities of Ethereum consensus?
Yeah, so you're asking about the details that Markham was going to talk about in his version of the talk.
Okay.
We actually have some write-up on that. So this engine, this model will run on multiple different substrates, and the architecture is such that you could migrate a vat of computation from one to another. On a system on EVM, there are some limits that mean we'll have to run a subset of it. But on a system without finality, when it's communicating with other systems that do have finality, you end up having to have finality gates. And so if I'm receiving a message from something that could back out, I might have that over a channel that says, and it's got to be 10 deep before I let the message through. Or there might be one where I really am going to run speculatively until it's 10 deep, and then I'll commit the transactions or things like that. So there are ways to do that, but it means exactly the same kind of, I want to surface that assumption, because when I'm making a hotel reservation, I just want to be able to know explicitly, semantically in my smart contract, how reliable is that confirmation.
Thanks.
If there's no more questions, that concludes this session. We will be going on a lunch break, and the next session is going to start at 2 p.m. It's going to be about the future of